which was the model that many of us experienced and the prevailing paradigm before the NGSS. So take a look at this slide and you can see the list of topics on the left and the phenomena on the right. And go ahead and add into the chat. What do you see as the difference? What is the difference with teaching with topics and teaching with phenomena? What might that look like in a classroom? I'll give you just a moment to think about and type about that. Okay, yeah, a lot of responses coming in, a lot of you saying fact-based versus curiosity-based. And in the phenomena, there are real-world applications. The phenomena encourage questions. They stimulate these questions about really why, like trying to get down into the deep into why something's happening, what's the cause of that. And they're authentic. Yeah, that's a nice way to put it. More engagement for students because they're relevant. Yeah, a few people said that they're specific and intriguing. Yeah, we've heard people say that they're very specific to one place or time like that. And many people have said too in the past, well, those phenomena can include the topics that are on the left, but they can also be broader. So they're broader, they can incorporate more than just those topics. There may be other ideas or other disciplines or other domains that come in when we're talking about the broader question of phenomena. So really nice responses to that. Thank you. And so really a key difference that we see when we're shifting to a phenomena-based teaching and learning is that it shifts the focus from learning about, as we saw in topics, to figuring out. And this has been the mantra that we've been leaning into as we're describing this shift, where topic-based approaches focused on learning about keep students in the role of a student. Whereas phenomena-based approaches focused on figuring out put students in the role of a scientist or an engineer. What figuring out does is it moves students to the center of the investigation. They are the ones figuring out phenomena. It provides natural motivation to seek out more information, to gather evidence in a variety of ways, to make sense of it, and to apply it to constructing the explanations of phenomena. Okay, so with that framing, we're going to move on to our next section, and I'll pass it back over to Leslie, who's going to take you through an example.
All right, thanks, Rebecca. And so we are going to jump into an example from Amplify Science to really illustrate the role of evidence in the phenomenon-based approach. And so before we dive into our instructional example, though, I want to provide a little bit of context and introduce you to the Amplify Science instructional approach. And so this really represents what we're trying to do in Amplify Science. And so this first circle is labeled Introduce a Phenomenon. And in the Amplify Science instructional approach, each unit starts off with a student. The student's taking on a role of a scientist or engineer, and are tasked with solving a problem related to a compelling real-world phenomenon. And so then the next circle says gather evidence from multiple sources. So through the course of the unit, students gather evidence, they gather different types of evidence. And the activities that we're going to be doing in this session, they're what we refer to as evidence sources. So next we have construct increasingly complex explanations. Students return to the unit's anchor phenomenon repeatedly throughout the unit, and they use what they figured out to explain the phenomenon. So typically this explanation, it's pretty incomplete early in the unit when the students haven't gathered all that much evidence. But as you can see from the blue arrows, these two circles repeat throughout the unit. And after a relatively simple explanation early in the unit, students gather enough evidence and they return to add complexity to their explanations. And then, so the final circle represents that at the end of the unit, students get a chance to transfer this understanding by explaining a related phenomenon. And so this general roadmap, it structures each Amplify Science unit. And so now we're going to zoom in and experience an example. So our example comes from the middle school unit called Chemical Reactions. And so acknowledging that the time we are in and that we're across the country, we're in a variety of instructional settings, we recognize that some of the activities like the hands-on experiences, they're more challenging to replicate in a remote teaching environment. And so really think about, as you experience the sequence, think about the role of evidence and where each activity fits with other evidence gathering activities that the students engage in as they work to figure out a phenomenon. So we'll be working on activities that come from the second chapter of the unit. So to avoid feeling like you're really jumping in the middle of halfway through a movie, I'm going to introduce you to the unit overall, and then we'll summarize what happens in that first chapter. And so, as I mentioned, in every Amplify Science unit, students take on the role of a scientist or engineer. And in that role, they work to explain a phenomenon and use what they figured out to solve a problem. So in this unit, the students take on the role of student chemists. And to find out about the phenomenon they'll work to explain, they receive an email from a Dr. Samara Young about a problem in a town called Westfield. And so in her email, Dr. Young explains that she received a call from a resident of Westfield who said that she turned on her faucet for a glass of water and a strange reddish brown substance came out. The residents said her neighbors were experiencing the same thing. So Dr. Young took some samples from the town water and from the well where the neighborhood's water comes from. And she found the reddish brown substance. It was in the town water, but it wasn't in the water from the well. But she did find that there was some fertilizer in the well water. So Dr. Young asked the student chemists for some help in finding out what the reddish brown substance is and where it came from. And so this is our anchor phenomenon. This anchor phenomenon, it needs to be rich and complex enough and with enough ideas embedded in it that it can motivate learning for an entire instructional unit. It needs to be specific to one event, kind of like as you all were referring to, that specificity of phenomena. And so for instance, we're not asking about chemical reactions in general. We're really focusing in on the mystery of a strange substance in a town's water. And so with that phenomena that we're trying to figure out, it's a big phenomenon and it's a complex one. So in our unit, we break it down and into different learning sequences called chapters. And so we're going to be, as I said, looking at a sequence from chapter 2. So I'll give you a quick overview of what students figure out in chapter 1 about that phenomena of the reddish brown substance in the pipes. So in the first part of the unit, the students are trying to figure out what that substance is. They investigate how substances are different, and they figure out that substances have different properties at the observable scale because they're different at the atomic scale. So that by the end of the chapter, they've analyzed that reddish brown substance, they've analyzed the pipes, they've analyzed the fertilizer, and they've discovered that each is a different substance with a different atomic structure. And then they go on to identify that reddish brown substance as rust. So with that brief on ramp, we're going to jump into our next chapter, chapter 2. And so after the students figure out that that substance is rust, Dr. Young asks for their help again in figuring out how that rust was formed. And she lets them know that she's done a little investigating herself and that other neighborhoods with similar well systems, they don't have rust in their tap water, but they also don't have fertilizer in their well water. So she has 3 claims about how that rust was formed, and she wants the student chemist to consider them. So the first claim is that the iron pipes changed into rust. The second claim is that the fertilizer changed to rust. And the third is that both the iron pipes and the fertilizer together changed into rust. And so remember, in chapter 1, students figured out that the iron, fertilizer, and rust, they're all different substances that have different properties because they are made of different repeating groups of atoms. And so we can't really conduct investigations in Westfield on those pipes, on that fertilizer, on that actual rust, but we can investigate and think about more general phenomena and then gather evidence around those and apply them back to the anchor phenomena. So notice that all three of those claims, they involve substances changing into another substance. So that's the first thing we can investigate. Is that even possible for a substance to change into another substance? And so to start answering the question, we're going to gather some evidence by observing what happens when two substances dissolved in water are mixed together. So just a reminder that students have figured out that different substances have different properties. So in our curriculum in Amplify Science, this is an activity that students do in the classroom, hands-on, they combine these substances, but these are not substances that they would have at home. So I turn to YouTube for a replacement video. But I will mention that Amplify Science, we're creating units for teachers and students to use in a remote or hybrid setting, and we're creating hands-on videos of all the hands-on activities. We just haven't made this one yet, so which is why I went to YouTube. So keep in mind, we're trying to collect evidence to answer the question, can substances change into different substances? So as you're watching this video, I want you to do a couple things. Observe the properties of each of the substances before they're combined. What do you notice about them? Then I want you to observe the properties of the substance or substances after they're combined. And then when we're finished observing, consider the question, did the substances change into different substances? So we're going to take a look. So remember, make some observations about each of these two substances before they're combined. And then we'll observe observations after they're combined. And then you can think, did that provide evidence that substances can change into other substances? So we'll jump back over here. And so you can imagine that our student chemists observing that the properties of the first two substances were both clear, and but then that the properties of the product substance was not the same. It was white, it was gel-like, that this provides some evidence that substances can change into other substances. So I'd like to pause right there. After our first activity, we gathered some evidence, and I want to ask you to think about this question. And remember that the students as student chemists are trying to explain how the rust forms. So based on this activity, and I want you to type in the chat what you think. What can we explain about the phenomenon of the rust in the pipes? And also think about what can't we explain. So go ahead and write your thoughts in the chat. What can we explain and what can't we explain about the phenomenon of the rust in the pipes? Wait a moment and see what we have. What can we explain based on that evidence gathering activity, and what can't we explain? And so what can we explain about that rust? And so we have seen that substances can change into different substances, but how can we apply that? Can't explain the color. Maybe the iron and fertilizer could be mixing together to make the rust. Okay, that we can explain that it's possible that the rust was formed by one substance changing to another substance, but we can't explain which substance changed into rust. And I like that. Can we explain how the color changed? And so there are some things that we can explain, but there's some things that we can't. So this activity, it provides something really valuable. And you can imagine, especially if it's hands-on, it shows the students real firsthand evidence that substances can change into other substances, which feels really meaningful. It shows the way that properties of a substance can change when that substance is combined with another substance. And that is evidence that it changed into another substance. But what it doesn't show students is how or why this happened, or provide a bridge between what they observed and the phenomenon that they're trying to explain. So it might lead students, like it did to some of you, to connect to rust and think that maybe a substance changed into rust, but it doesn't lead them to any conclusions about how the rust formed. And it also doesn't lead students to understand why these two liquids in particular, when they were mixed together, they formed a solid substance, but that when two other clear liquids formed together might not form a solid substance. And so I'm going to use this diagram to contextualize the evidence gathered in the mixing substances activity and with what we do next. So we started out, as we've been talking about, by thinking about the phenomenon in Westfield. And the big thing that we're trying to explain is how the rust formed in the pipes. And remember, we have those three claims about where it might have come from: the pipes, the fertilizer, or the combination. And so in order to start to figure out what happened, we are trying to figure out if substances can change into other substances. And so we're starting to collect evidence and multiple sources of evidence. And so we did that hands-on activity, and it gave us some evidence. But as we talked about, it doesn't provide us a complete answer to the question. And in particular, we have no idea what happened at the atomic scale. So students need more evidence. So next, they use a digital simulation to test combining those same substances and to observe what happens at the atomic scale. So I'm going to jump over here into our the chemical reaction sim that we have in Amplify Science. All of our units in middle school have a simulation that students use. And so we're going to combine the same two substances. So I'm going to get calcium chloride and sodium carbonate. I'm going to show the properties. So they're similar, but they definitely have some different properties. And so we're going to test them out and see what happens when we combine them. You can see they're being combined. We have the lab conditions right here. And you also see there's a visualization of what is happening at the atomic level. And so let's take a look at our results. And our results show that there are two new substances, sodium chloride and calcium carbonate. And so let's review what happened. I'm going to show the atomic scale here too. We can see that the calcium chloride and the sodium carbonate, there was a chemical reaction and they changed into different substances. And you can also see that at the atomic scale, those atomic structures for each of those substances are different. And so we're going to jump back. And so students now have more evidence, and they have some evidence about what is happening at the atomic level. And so after gathering these couple different pieces of evidence, students discuss with a partner what they've gathered and how that relates to the investigation question. And so this discourse is so important for the students for making sense of that evidence. And students synthesize what they observed in the sim with what they observed in the hands-on investigation, and they now have evidence at both that macroscopic and the atomic scale that substances can change into other substances. And this leads them to a key concept, so an important idea that answers the investigation question, that during a chemical reaction, one or more starting substances, the reactants, change into one or more different substances, with the products. And so now that the students know that substances can change into other substances, they're closer to explaining how the rust formed, but that explanation isn't complete. So they haven't figured out how substances change to different substances during the chemical reaction. And so this leads to a new investigation question. How do substances change into different substances during chemical reactions? And so to figure out the investigation question and more fully explain the phenomenon, students need to continue gathering evidence. And you likely notice that further investigating in the sim could provide evidence to begin to figure out how substances can change into different substances. And so that's what happens. Students use the sim to combine substances that do and do not form different substances when they're combined, and they look for patterns at the atomic scale. And then they also work with physical models and have class discussions to figure out ideas about how substances change into different substances. So at this point, students have figured out some really important ideas: that atoms don't change from one type to another, and that in a chemical reaction, atoms rearrange themselves to form different groups of atoms. So they're starting to develop a causal understanding, and they can use what they figured out over the investigations in the chapter to create a model of the chemical reaction in the pipes. And so then they can use this model to help them evaluate the claims about where the rust came from, and use this as evidence to explain the phenomenon about how the rust formed. So in the classroom, students would manipulate tokens to test each of these claims, seeing if the atoms of each substance can rearrange to form rust. I'm going to use a modeling tool to show you how students would do this. But at home, like if it was in a remote setting, students could use coins or use small pieces of paper to do this same sense-making activity. So we're going to jump back over here. And so you can see I have modeled our iron pipes, our fertilizer, and then down here is a model of the atomic structure of the rust. And so I want to use my model to test each of those claims. So can I make the rust with just the iron pipe atoms? And I can't, because I'm missing oxygen. And can I make the rust with just the fertilizer, the atoms in the fertilizer? I can't, because I'm missing the iron. But if I take the iron from the iron pipes and the oxygen from the fertilizer, then I can make the rust. And so using this model, I can apply the things I figured out to show and have evidence for the claim that the iron pipes and the fertilizer changed into rust. And so, armed with that evidence and that they've generated with their model, and then their understanding of those key concepts that they developed through engaging with the evidence from the hands-on and the sim investigations, students are ready to construct an explanation of the Westfield phenomenon. And here's an explanation they could come up with. I believe the rust formed from a chemical reaction between the iron pipes and the fertilizer. I know that atoms in substances can rearrange during a chemical reaction, so the iron atoms from the pipe must have combined with the oxygen atoms from the fertilizer to make the rust, which is made up of iron and oxygen atoms. And so they've constructed a causal explanation of how that rust was formed. And so with that really quick example, let's take a moment to reflect on the role of evidence in phenomenon-based instruction. And so remember that the NGSS call for that phenomenon-based teaching and learning, and with the goal being to develop the general science ideas, but based on evidence that can explain and predict phenomena. So this diagram is one way to show how in our curriculum that connection between evidence and phenomena. So this is, you'll kind of see it is familiar, is the final version of the diagram I've been showing you. And it illustrates the generalized architecture of a chapter in Amplify Science, including how students use evidence sources in different modalities to figure out key concepts, which they apply to construct an explanation of the phenomena. And in other words, they're figuring out like a scientist. And so, but let's dive a little more deeply and consider the activities we just did. We did a hands-on, or at least virtually observed a hands-on investigation. We used a sim to combine substances, and we created a physical model of a chemical reaction. And when you consider each as an activity on its own, they each absolutely offer students the opportunity to learn something about chemical reactions. And using 2 or 3 together probably has even more of an impact. But when we're thinking in terms of evidence, it's not just about using the activities in combination. I would argue that when each of these activities becomes a source of evidence for figuring out a phenomenon, students develop a deeper understanding of the science concepts than they would have if they just did each of these activities, because they're doing it for a purpose. And they also experience science as a way to think about and make sense of the world, taking steps towards developing into those evidence-based science thinkers that we've talked about at the beginning of the session. And this slide shows the different evidence sources students use in the chemical reaction unit. And some happened in the chapter I talked you through, others happened in other parts of the unit. But it doesn't just show the evidence sources, it shows how the students are engaging with those sources. And so as students are engaging with these evidence sources, they're not only figuring out science ideas like a scientist, but they're also experiencing being evidence-based thinkers. And the different ways that the students gather, engage with, and make sense of evidence is tied to that broad range of science and engineering practices that are outlined in the NGSS. And students who are figuring out phenomena with a variety of evidence sources will be engaging in these practices. And so I want to return to what we talked about at the beginning about why we teach science. And we're going to take a look at a quote from the NRC framework. That's the document that informed the design of the NGSS. And it says, understanding science now more than ever is essential for every American citizen. Science permeates every aspect of modern life. Some knowledge of science is required to engage with the major public policy issues of today, as well as to make informed everyday decisions such as selecting medical treatments or determining how to invest public funds. In these contexts, learning science is important for everyone, even those who eventually choose careers in fields other than science and engineering. And what really resonates with me about this quote is how far it reaches. Everyone needs to have some knowledge of science, because science is not just a body of knowledge, but it is a way of thinking about and understanding the world. And as science educators, providing opportunities for students to engage with multiple sources of evidence as they make sense of and explain phenomena can support them in developing a deep understanding of science and in becoming the curious, skeptical, evidence-based thinkers capable of making decisions that improve their and their communities' lives. And so with that, I'm going to pass it back over to Rebecca. Rebecca.
Lovely for all of that. Yep. I was on mute. So yeah, that was great. The goal of our talk today was to deepen your understanding of the role of evidence in the NGS era, and hopefully experiencing that sequence from chemical reactions helped you do that. And we were glad to share the rationale behind the phenomenon-based approach of Amplify Science. And so one purpose of understanding this rationale behind the program is to help you make principled decisions about how to apply these ideas in different contexts, including our current situation where most of us are teaching in a remote setting. And so we'd really encourage everyone to keep these approaches in mind when you are making adaptations. So one thing to use it as an example is in the last few months, the team at the Lawrence, in collaboration with Amplify, has been adapting our regular Amplify Science materials to be workable in remote settings. We've adapted the format, but we've worked to keep the same phenomenon-based approach. What we've been doing is working to design these materials for a wide range of implementation scenarios that are happening. And all of you on this call probably have something different from one another. Some people are using Amplify Science or trying to use it in its full form. There's others who are faced with reduced instructional time for science. And of course, there's a huge variety in what access to digital tools their students have and how much support students have in their home settings. So with that in mind, the teams have created two types of materials. One is called the at-home units, and the other is the teacher taught at-home videos. Now the at-home units are trimmed versions of a full unit. We know there isn't as much time during remote instruction in most places, and these materials can be pushed out to students either digitally or made into print packets where everyone should have access to the videos either on a digital device or hopefully on a phone. And then we have another set of resources called the at-home videos. Now these are the full amount of the Amplify Science lesson where a teacher is filming themselves at home. They encourage students to pause the video and engage with some of the investigations by thinking or talking to someone. And so zooming into the at-home units, even though the Amplify Science at-home units are the condensed versions of the Amplify Science units, we've designed them so that we can preserve the anchoring phenomena and the coherent structure that Leslie just showed you how that students would work through. This includes that students are using multiple sources of evidence to figure out phenomena. But of course, like you saw in this session today, we've had to adapt the evidence sources. Some sources of evidence, such as simulations or articles, can adapt well to working with students remotely, especially if digital access isn't an option, we've had to modify some of the way that students get that evidence. And for our hands-on activities, like we've mentioned, these are either revised so that it works with different materials, such as everyday materials kids might have at home, or a video could be provided so students still get what they need to figure out the phenomena. And so if you're not using Amplify Science, that's okay. We'd still encourage you to think about this phenomenon-based structure and be thinking about starting with phenomena, not to abandon this approach or this structure, even if you don't have the same materials that you've had before. Because whether it's a complex anchor phenomena like the reddish-brown substance in the town water, or maybe it's a smaller investigative phenomena such as the substances changing into other substances, starting with the phenomena allows students to put themselves in that situation where they're seeing themselves as scientists. You will have to plan for how to provide some of those important evidence sources and think about what resources can you use so that they are able to figure out. Are there books or observations or videos of hands-on activities or digital tools like simulations that they can engage with? So we wish you good luck in making these adaptations as you go forth. And we're going to stop there with our presentation and open it up for Q&A. I didn't get any chats of questions in the chat so far. So if you have anything you want to ask, feel free to go ahead and put it in the chat right now.
I just got a direct question about, is Amplify Science a curriculum? How do I find out more about it? And I'm wondering if Nick can jump on and explain how attendees can find out more about Amplify Science at NSTA. Let's see if Nick is still on.
I know there is a booth, there is a virtual booth that everyone can go to, and I think Nick would be the person to talk to as well, to be able to find out more about actually piloting that or trying it out, which is what many districts that we've worked with have done before they've decided to jump in and adopt it. They definitely like to try it out. We'll wait just another moment to see if others have questions. We must have answered them all.
I see, do most of your other lessons start with a scenario? And so all of our units are centered around an anchor phenomenon. So all of our units, the students are introduced to a phenomenon, like in this example, they were introduced to the idea of this strange substance in a town's water system. And then throughout the unit, we break that down into smaller phenomena for each chapter, but they're always working towards figuring out what's going on with that particular phenomena.
Yeah, so they all start with a scenario, as you said, where they find out that something has happened in a specific place and time, and they take on a role to try to figure it out. So they're usually in a role of a scientist, some kind of scientist. We say, now you're all, what are they in this unit? They're chemists, student chemists.
Yes.
And in others, they might be, and there's others that they're like forensic meteorologists, or they take on the role of an engineer, and they in that role, and it's up to the teacher how much they play up that role. But in that role, they have to do the figuring out.
All right. So there's
Go ahead.
No, go ahead, Rebecca.
I was going to see if you had an answer to this. Could phenomena be hypothetical, such as they don't have a true answer yet, and it's more open? And yeah, I think you're catching on that. Yeah, phenomena, because they're the things in the natural world that we're curious about, they don't always have an answer. The scientists have figured out a lot about a lot of the science in our world, but even scientists haven't figured out everything there is to know. So the hypothetical phenomena is a good way to have it be more open-ended. And we, in fact, have a part of each of our units where there isn't one answer, that we present a second scenario where kids have to apply their knowledge to a new scenario. And those are intentionally designed to be, to not have one right answer. Did you have more to add?
No, I don't, but someone asked about an evaluation, and there's not an evaluation to fill out. Is that correct?
I have not seen one. I wish we could say yes and provide you with one. Maybe at the NSTA session splash page, there is one to fill out, but we don't have one directly to have you. But if you find one, please do fill it out, because that always does help us know how we did and help NSTA know that if you'd like sessions like this again. So please do look for one if there is one. Someone asked, sorry, Leslie, go ahead. I'll let you
are there free, if you just look under, I think, do an internet search under NGSS phenomena, there are a number of online resources that list many different kinds of phenomena.
And I think even NSTA has a really great resource on their NSTA website. Oh, Sandra, I see your point. The moderators provided one. Yeah, we joined this within our group and didn't have an NSTA moderator. So sorry that we don't have an evaluation for you to fill out. TCTs also give you phenomena. I don't know what TCT is, if Mona wants to explain that.
There is an.
Oh, there we go.
Put in. So yeah, there are a number of resources out there.
I thought I saw one more question come in. Maybe not. Oh, such as life on Mars. Someone had a comment. Yeah, life on Mars that we don't know. That's a very open-ended, still question for everyone. Oh, good resources that folks are sharing. NSTA's daily dues designed for distance learning and in person. And then to answer the question, is your presentation available? Yes, I think these are all being recorded and available for folks to use as recorded sessions afterwards. All right, well, I think we didn't see any more questions coming up, but really thank you everyone for sharing the resources that you're sharing right now. We want to really thank you for your participation and wish you the best of luck in your NSTA sessions for the rest of the weekend, and hope you have a great time. Thank you for joining.